Beneath your feet right now lies a mystery that could shatter everything we think we know about our place in Earth's history. What if humans weren't the first intelligent species to build cities, harness energy, and reshape this planet? What if millions of years before we discovered fire, another civilization rose from the primordial depths, built vast technologies we can't even imagine, and then vanished without a trace? Today, we're diving into one of the most mind-bending scientific thought experiments ever proposed: the Silurian Hypothesis. Named after fictional reptilian beings from Doctor Who, this isn't science fiction anymore. It's a legitimate scientific framework that asks a question so profound, it's forcing researchers to completely rethink how we study Earth's deep past and search for life on other worlds. Prepare yourselves. We're about to journey through geological time itself, examining evidence that could rewrite the story of intelligence on Earth. We'll explore why finding traces of ancient civilizations is nearly impossible, what signatures they might leave behind, and why this question is crucial for understanding our own future and the search for alien life across the cosmos. But first, let me tell you why this matters more than you might think. The implications of the Silurian hypothesis extend far beyond academic curiosity. If we can't definitively prove that previous civilizations didn't exist on Earth, how can we hope to detect signs of life and intelligence on distant exoplanets? This thought experiment is revolutionizing astrobiology, climate science, and our understanding of what makes a planet habitable. We begin with a simple yet staggering realization about time itself. Picture the entire history of complex life on Earth compressed into a single year. Dinosaurs would appear in early December and vanish on Christmas Day. Human civilization would occupy only the final few seconds before midnight on New Year's Eve. Our industrial age, the period when we began burning fossil fuels and reshaping the planet's chemistry, would last less than the blink of an eye. This perspective reveals something profound about the nature of technological civilizations. We've existed as a species for roughly 300,000 years, but we've only possessed industrial technology for about 300 years. That's just 1/10 of our species' existence, and an almost incomprehensibly small fraction of the time-complex life has existed on Earth's surface. Complex life has thrived on our planet for approximately 400 million years. During this vast expanse of time, countless species have evolved, flourished, and disappeared. Some achieved remarkable intelligence. Dolphins developed sophisticated communication systems. Octopi demonstrate problem-solving abilities that rival many vertebrates. Some dinosaurs possessed brain structures, suggesting advanced cognitive capabilities we're only beginning to understand. Yet as far as we know, only one species ever developed the ability to harness energy on a planetary scale, to split atoms, to send signals across interstellar space, to fundamentally alter the chemistry of the atmosphere itself. Only humans crossed that invisible threshold from biological intelligence to technological civilization. But here's the question that keeps scientists awake at night. If it happened once, could it have happened before? The Silurian hypothesis emerged from the brilliant minds of astrophysicist Adam Frank and climate scientist Gavin Schmidt in 2018. These researchers weren't claiming that ancient civilizations actually existed. Instead, they were asking a more subtle and powerful question. If a technological civilization had existed on Earth tens of millions of years ago, would we be able to detect it with our current scientific methods? The answer, as we're about to discover, is far more complicated than you might expect. Frank and Schmidt approached this question with the rigor of true scientists. They defined civilization not by culture, art, or philosophy, but by energy consumption. A technological civilization, in their framework, is one that can harness and manipulate energy on scales that affect planetary systems. By this definition, humans only became a true technological civilization around the time of the Industrial Revolution. This energy-based definition is crucial because energy use leaves traces. When you burn fossil fuels, you change atmospheric chemistry. When you split atoms, you create isotopes that don't exist in nature. When you manufacture materials on industrial scales, you scatter synthetic compounds across the globe. These signatures can persist in geological records for millions of years, long after every building has crumbled and every artifact has turned to dust. But detecting these signatures requires us to overcome one of the most fundamental challenges in all of paleontology, the problem of deep time preservation. Most people imagine the fossil record as a comprehensive library of Earth's biological history. In reality, it's more like a collection of random pages scattered from millions of books, with most chapters missing entirely. The processes that preserve evidence of past life are extraordinarily rare and selective. Consider what it takes for something to become fossilized. First, an organism must die in exactly the right environment. Rapid burial in sediment, protection from scavengers and decay, the precise chemical conditions that allow organic material to be replaced by minerals over geological time. Even under ideal circumstances, fossilization is incredibly uncommon. For complex organisms with hard parts like shells or bones, the fossilization rate is estimated at less than 1 in 10,000. For soft-bodied creatures, the odds are almost impossible. For technological artifacts made of metal, plastic, or other synthetic materials, the preservation challenges become even more extreme. Now consider the temporal resolution problem. Even if something does get fossilized, the geological record doesn't preserve every moment in time with equal fidelity. Most sedimentary rocks represent long periods of accumulation, interrupted by gaps where no material was deposited or where existing layers were eroded away. The average temporal resolution of the geological record is measured in thousands to millions of years. This means that even if an industrial civilization lasted for thousands of years, it might appear as nothing more than a brief anomaly in a single thin layer of rock. A technological society that rose and fell within a few centuries might leave no detectable geological signature at all. This preservation bias becomes even more problematic when we consider the age of Earth's exposed surface. Plate tectonics constantly recycles the planet's crust. Oceanic plates are subducted back into the mantle within 200 million years. Continental surfaces are weathered, eroded, and buried beneath newer deposits. The oldest exposed rocks on Earth's surface date back only about 4 billion years, and most accessible geological formations are much younger. The oldest place on Earth's surface, a stretch of Israel's Negev desert, is just over 1 million years old. This means that direct evidence of surface civilizations older than a few million years would be extraordinarily difficult to find, even if they had existed, But the preservation challenges go even deeper than simple age. The geological record is not uniformly distributed through time. There's something paleontologists call the pull of the recent. The quality and quantity of fossil records decline dramatically as we look further back in time. This happens for several reasons. Older rocks are more likely to have been subjected to metamorphism, heat, and pressure that destroy original structures. They're more likely to have been uplifted and eroded away. They're less likely to be accessible at the surface where we can study them. Even more problematic is the concept of doomed sediments. Most sedimentary deposits that form today will never survive into deep geological time. They'll be eroded, subducted, or otherwise destroyed within a few million years. Only sediments deposited in very specific environments have a reasonable chance of preservation over tens of millions of years. This creates a secular trend in the geological record. The further back in time we look, the less evidence we have, not necessarily because less was happening, but because less has survived for us to study. For terrestrial life, the preservation problems are even more severe. Marine environments provide much better conditions for fossilization than terrestrial ones. Land surfaces are subject to weathering, erosion, and oxidation that quickly break down organic remains and artificial materials. This is why the marine fossil record is relatively rich compared to the terrestrial record. But technological civilizations, by definition, are more likely to leave their primary signatures on land surfaces where they build cities, extract resources, and concentrate their industrial activities. Consider what would happen to our own civilization if humans disappeared tomorrow. Within a few hundred years, most buildings would collapse, metal structures would rust away, plastic materials would begin to break down under ultraviolet radiation and oxidation. Within a few thousand years, very little direct evidence of our cities and infrastructure would remain on the surface. After a few million years, with plate tectonics at work, what was once on the surface would be at the bottom of the sea, while ancient ocean floors would have become mountain peaks. The entire geography of the planet would be fundamentally transformed. This doesn't mean that all evidence would disappear, but it does mean that we need to look for very different types of signatures than the obvious artifacts we might expect to find. Given these preservation challenges, Frank and Schmidt realized that searching for direct evidence of ancient civilizations was essentially hopeless. Instead, they focused on indirect signatures that might survive the ravages of geological time. The most promising approach involves looking for chemical anomalies in sedimentary rocks. Industrial civilizations necessarily consume energy on massive scales. They burn fossil fuels, altering the carbon cycle. They extract and concentrate rare elements, changing the natural distribution of metals and minerals. They create synthetic compounds that don't exist in nature. These chemical changes can leave signatures in sedimentary layers that persist long after the civilization itself has vanished. Unlike fragile artifacts or structural remains, chemical signatures become incorporated into the rock record itself, where they can survive for millions of years. The key insight is that technological civilizations don't just use energy, they use it in ways that create distinctive patterns in the geological record. Natural processes can also cause dramatic changes in atmospheric chemistry and elemental distributions, but they typically operate on different timescales and produce different signatures than industrial activities. This leads us to one of the most important aspects of the Silurian hypothesis. It's not enough to find anomalies in the geological record. We need to develop criteria for distinguishing between natural phenomena and potential technological signatures. Natural climate changes, volcanic eruptions, asteroid impacts, and biological innovations can all create dramatic shifts in atmospheric chemistry and sediment composition. The Earth has experienced numerous periods of rapid warming, mass extinctions, and geochemical upheavals throughout its history. But technological signatures should have certain distinctive characteristics. They should be relatively rapid in geological terms, occurring over thousands rather than millions of years. They should show evidence of coordinated global changes rather than regional variations. They should involve elements and compounds that are rare in natural processes but common in industrial activities. Most importantly, they should show evidence of what scientists call energy intensification. Natural processes tend to work with the energy flows that already exist in environmental systems. Technological processes concentrate and redirect energy in ways that create unusually intense local effects. This brings us to one of the most fascinating aspects of the Silurian hypothesis. To understand what ancient technological signatures might look like, we need to study the signatures that our own civilization is currently creating. The modern era, which geologists call the Anthropocene, provides a perfect template for understanding how industrial civilizations impact planetary systems. Since about 1950, human activities have begun to create geological signatures that will persist for millions of years. We've doubled the amount of fixed nitrogen on the planet through industrial fertilizer production. We've created a hole in the ozone layer through industrial release of chlorofluorocarbons. We've pumped enough greenhouse gases into the atmosphere to cause planetary-scale climate change. We've created tens of thousands of synthetic compounds that don't occur naturally anywhere on Earth. These changes are happening so rapidly and on such a scale that they're creating what geologists call a golden spike in the rock record. Future geologists studying sediment cores millions of years from now will be able to identify a sharp transition in the mid-20th century when human industrial activity fundamentally altered planetary chemistry. The appearance of manufactured materials in sediments, including aluminum, plastics, and concrete, coincides with global spikes in radioactive isotopes from nuclear weapons testing and particulates from fossil fuel combustion. Carbon's, nitrogen, and phosphorus cycles have been substantially modified. New minerals and rock types are forming from industrial waste products. This comprehensive transformation of planetary systems is what a technological civilization looks like from a geological perspective. It's not just about building cities or creating artifacts. It's about fundamentally altering the chemical and physical processes that operate on planetary scales. But here's where the story takes a surprising turn. When we look back through Earth's geological history with this new perspective, we find that similar rapid changes have occurred multiple times in the past. The question becomes, how do we tell the difference between natural catastrophes and potential technological signatures? The most famous example is an event that occurred about 56 million years ago, during a period geologists call the Paleocene-Eocene thermal maximum, or PETM. This event provides a crucial test case for the methodology of the Silurian Hypothesis. During the PETM, global temperatures rose by 5 to 8 degrees Celsius in just a few thousand years. Massive amounts of carbon were released into the atmosphere and oceans. Sea surface temperatures in the Arctic reached 23 degrees Celsius, comparable to modern subtropical waters. There were widespread extinctions in both marine and terrestrial ecosystems. At first glance, the PETM might seem like evidence of an ancient technological civilization. The rapid warming, the massive carbon release, the global environmental disruption all bear some resemblance to what we're seeing from human industrial activity today. But detailed analysis reveals crucial differences. The PETM unfolded over about 200,000 years, while our current climate changes are happening in just a few centuries. The carbon isotope signatures suggest volcanic sources rather than fossil fuel combustion. Mercury levels in sediments point to massive volcanic eruptions from the North Atlantic igneous province as the likely trigger. The PETM demonstrates both the promise and the challenges of the Silurian Hypothesis methodology. Natural processes can indeed create dramatic, rapid changes in planetary systems, but they tend to operate on different timescales and through different mechanisms than technological processes. This raises a profound question about the nature of planetary catastrophes and the role of intelligence in cosmic evolution. How often do planets experience rapid environmental changes? How often might these changes be triggered by technological civilizations rather than natural processes? These questions become even more intriguing when we consider that some geological events remain poorly understood. There are periods in Earth's history marked by rapid changes in atmospheric chemistry, unusual isotope signatures, and mass extinctions that don't have clear natural explanations. Could any of these represent signatures of previous technological civilizations? The honest answer is that we don't know. Our current methods aren't sophisticated enough to make definitive determinations, and our understanding of deep-time geological processes is still evolving. But the Silurian Hypothesis isn't really about proving that ancient civilizations existed. It's about developing the scientific framework and methodological tools that would allow us to detect them if they had. In the process, it's revealing profound insights about the relationship between intelligence, technology, and planetary evolution. The implications extend far beyond Earth's history. If we can't definitively detect technological signatures on our own planet, how can we hope to identify signs of intelligence on exoplanets thousands of light years away? The search for extraterrestrial intelligence requires us to understand what technological civilizations look like from a planetary perspective. This brings us to one of the most exciting frontiers in modern astronomy. As we discover thousands of exoplanets and develop increasingly sophisticated methods for analyzing their atmospheres, we're beginning to search for what scientists call technosignatures, chemical or physical evidence of technological activity that might be detectable across interstellar distances. The Silurian Hypothesis provides crucial guidance for this search. It suggests that the most detectable signatures of technological civilizations might not be radio signals or megastructures, but rather the chemical fingerprints of industrial activity in planetary atmospheres. But there's another class of evidence that might survive much longer than anything on Earth's dynamic surface. What if ancient civilizations were spacefaring? What if they left artifacts in more stable environments where geological processes couldn't erase them? This possibility leads us beyond Earth itself to the Moon, Mars, and other bodies in our solar system where evidence might persist for hundreds of millions or even billions of years. The Moon hangs in our night sky like a cosmic museum, its airless surface preserving footprints left by Apollo astronauts over half a century ago. Those bootprints will remain clearly visible for millions of years, protected by the vacuum of space from the wind and weather that would erase them on Earth within decades. This remarkable preservation potential has led some researchers to wonder, could the Moon harbor evidence of civilizations that predated humanity by geological ages? Penn State astronomer Jason Wright has become a leading advocate for expanding the search beyond Earth's dynamic surface. His reasoning is elegantly simple. Habitable planets like Earth are remarkably efficient at destroying things left on their surfaces. Plate tectonics, which recycle the crust. Weather systems erode structures. Biological processes break down materials. But celestial bodies without atmospheres or geological activity preserve evidence with startling fidelity. Consider what this means for the deep history of intelligence in our solar system. If dinosaurs had somehow developed spaceflight 100 million years ago, remnants of their technology might still exist in stable lunar orbits or buried beneath the Moon's regolith. The same preservation principle applies to Mars, asteroids, and other geologically inactive bodies throughout the solar system. The implications become even more intriguing when we consider the possibility of interplanetary civilizations. Earth-based industrial societies might have established mining operations on asteroids, research stations on Mars, or manufacturing facilities in the vacuum of space where certain processes work more efficiently than in planetary atmospheres. These extraterrestrial installations could survive for hundreds of millions of years, long after every trace of the parent civilization had vanished from Earth's surface. Future archaeologists might find more evidence of ancient technological activity by exploring other worlds than by digging through terrestrial sediments. But the search for ancient artifacts faces its own methodological challenges. How do you distinguish between natural rock formations and artificial structures after millions of years of micrometeorite bombardment and radiation exposure? How do you recognize technology based on principles we haven't discovered yet? These questions bring us back to the fundamental challenge of the Silurian Hypothesis. We're looking for evidence of something using conceptual frameworks developed by the very civilization we're trying to detect predecessors for. It's like trying to find a book written in a language you don't know, using an alphabet you've never seen. This limitation becomes particularly relevant when we consider the possibility that ancient civilizations might have developed along completely different technological pathways than our own. We tend to assume that all technological development follows patterns similar to human history. Stone tools, agriculture, metallurgy, fossil fuels, electronics, nuclear power. But evolution demonstrates that similar problems can be solved through radically different biological strategies. Flight evolved independently in birds, bats, and insects using completely different anatomical approaches. Echolocation appeared separately in dolphins and bats through different neural mechanisms. Vision evolved dozens of times using various optical principles. If biological evolution can find multiple solutions to the same challenges, why shouldn't technological evolution follow similar patterns? Ancient civilizations might have developed energy systems based on principles we haven't discovered. They might have created materials using processes we can't imagine. They might have solved fundamental engineering problems through approaches that wouldn't occur to human minds. This possibility makes the detection challenge exponentially more difficult. We're not just looking for signatures of technology. We're looking for signatures of potentially alien technology that operated according to different physical principles and left behind evidence that might not match our expectations. The problem becomes even more complex when we consider the temporal aspects of technological development. Human industrial civilization has existed for roughly 300 years out of our species' 300,000-year history. That's 1/10 of 1% of our total existence as a recognizable species. If this ratio represents a typical pattern, then technological phases might be extraordinarily brief compared to the biological lifespans of intelligent species. A civilization might develop industrial capabilities, flourish for a few centuries or millennia, then transition to something completely different that leaves no geological signatures. Perhaps advanced civilizations learn to work within natural energy flows instead of disrupting them. Maybe they develop technologies that integrate seamlessly with biological and geological processes. They might achieve sustainability levels that eliminate the chemical signatures we associate with industrial activity. This raises profound questions about the relationship between technological advancement and environmental impact. We tend to assume that more advanced civilizations would necessarily leave larger footprints on planetary systems. But what if the opposite is true? What if technological maturity is measured by how little disruption a civilization causes to its planetary environment? From this perspective, the absence of clear technological signatures in the geological record might not indicate that ancient civilizations never existed. It might indicate that they became so sophisticated that their activities became indistinguishable from natural processes. This line of thinking leads to one of the most unsettling implications of the Silurian Hypothesis. If advanced civilizations learn to operate without leaving detectable traces, then the universe might be filled with intelligence that remains completely invisible to our current detection methods. The search for extraterrestrial intelligence has focused primarily on radio signals, optical flashes, and megastructures that would be obvious signs of technological activity. But if civilizations routinely transition beyond the phase where they produce such signatures, then we might be looking in entirely the wrong places. This possibility transforms our understanding of the so-called Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and our failure to detect any evidence of it. Perhaps the galaxy is teeming with civilizations that have learned to develop without disrupting the natural systems that support them. But let's return to Earth and examine the types of evidence that might actually survive geological timescales. While direct artifacts are unlikely to persist, certain technological signatures could remain detectable for millions of years under the right preservation conditions. Nuclear technology represents perhaps the most unambiguous class of technological signatures. When humans began testing nuclear weapons in the 1940s, We created isotopes that simply don't exist in nature. Cesium-137, plutonium-239, and plutonium-240 will persist in the environment for thousands of years, creating clear markers of artificial nuclear reactions. Even more significantly, these isotopes have been dispersed globally through atmospheric testing. Future geologists studying sediment cores millions of years from now will find a sharp spike in artificial radioactivity that coincides precisely with the mid-20th century. This nuclear signature will be detectable long after every nuclear weapon has been dismantled and every power plant has been decommissioned. The persistence of nuclear signatures provides a template for detecting ancient technological activity. If previous civilizations developed nuclear technology, they would have left similar isotopic anomalies in the geological record. The absence of such signatures in ancient rocks suggests either that previous civilizations never developed nuclear capabilities, or that they used fundamentally different approaches to nuclear physics. But nature provides its own nuclear signatures that complicate this analysis. The Oklo reactors in Gabon demonstrate that nuclear fission can occur naturally under very specific geological conditions. About 2 billion years ago, uranium deposits with just the right composition and geometry sustained nuclear chain reactions for hundreds of thousands of years. These natural reactors created many of the same isotopes that artificial nuclear reactions produce. However, they didn't generate significant quantities of the long-lived transuranic elements that characterize weapons testing and nuclear power production. The isotopic signatures are subtly different, providing a baseline for distinguishing between natural and artificial nuclear activity. This distinction becomes crucial when evaluating unusual isotopic anomalies in ancient rocks. There are geological formations that contain unexpected concentrations of rare elements and unusual isotope ratios. Some of these anomalies have clear natural explanations involving hydrothermal processes, meteorite impacts, or unusual biological activity. Others remain poorly understood. Could any of these represent signatures of ancient nuclear technology? The honest answer is that our current analytical methods aren't sophisticated enough to make definitive determinations. We need more sensitive instruments, better theoretical models, and more comprehensive surveys of the geological record. The development of these capabilities has implications far beyond the Silurian Hypothesis. The same techniques that could detect ancient technological signatures on Earth would be invaluable for analyzing samples from Mars, Europa, Enceladus, and other potentially habitable worlds in our solar system. If we're going to search for life and intelligence throughout the cosmos, we need to understand what their signatures look like and how long they persist under different environmental conditions. Earth serves as our only laboratory for testing these methodologies, but nuclear signatures represent just one category of potentially detectable technological evidence. The mass production of synthetic materials creates another class of long-lasting markers that could survive geological timescales. Since the 1950s, humans have produced over 9 billion tons of plastic. These synthetic polymers are now distributed throughout every environment on Earth, from the deepest ocean trenches to the highest mountain peaks. Microplastics have become ubiquitous markers of human industrial activity. Unlike organic materials that decompose relatively quickly, many plastics are designed to resist degradation. They can persist in the environment for hundreds or thousands of years before breaking down into smaller fragments. Even then, the chemical signatures of polymer breakdown products might remain detectable in sediments for much longer periods. The global distribution of plastics creates what geologists call a stratigraphic marker for the Anthropocene epoch. Future researchers will be able to identify mid-20th century sediments by their distinctive plastic content, much like current geologists use fossil assemblages to date ancient rock formations. This preservation potential suggests that ancient civilizations with advanced materials science might have left similar signatures in the geological record. Synthetic compounds that don't occur naturally would stand out clearly in chemical analyses of ancient sediments, but the absence of such signatures in rocks older than a few million years raises intriguing questions. Either previous civilizations never developed advanced materials science, or they created materials so different from our plastics that we wouldn't recognize them as artificial. There's also the possibility that ancient synthetic materials have already been discovered but misidentified as natural minerals. The geological record contains thousands of mineral species, many of which are rare and poorly understood. Could some of these represent the degraded remains of artificial compounds created by previous civilizations? This question highlights one of the fundamental challenges in applying the Silurian hypothesis. We're looking for anomalies in a system we don't fully understand. Earth's geochemistry is extraordinarily complex, with countless processes that can create unusual elemental concentrations and isotopic signatures. Distinguishing between exotic natural phenomena and potential technological signatures requires comprehensive knowledge of how geological, biological, and atmospheric systems interact over millions of years. We're still developing this understanding for our own planet, let alone for the exoplanets, where we hope to search for signs of life and intelligence. The challenge becomes even more daunting when we consider the possibility that ancient civilizations might have deliberately concealed their technological signatures. If a species developed sufficient understanding of geological processes, they might have designed their industrial activities to minimize long-term environmental impacts. Advanced recycling technologies could eliminate waste products. Renewable energy systems could avoid the carbon signatures associated with fossil fuel consumption. Biological manufacturing processes could create materials that degrade naturally without leaving artificial residues. From this perspective, the absence of clear technological signatures in ancient rocks might actually indicate the presence of highly sophisticated civilizations that learned to develop sustainably. The most advanced societies might be precisely those that leave the fewest traces for future archaeologists to discover. This possibility has profound implications for our own civilization's development trajectory. If sustainability represents the hallmark of technological maturity, then our current approach to industrial development might represent a primitive phase that advanced civilizations quickly outgrow. The Silurian hypothesis thus becomes more than just a thought experiment about Earth's deep past. It becomes a mirror for examining our own relationship with planetary systems and a guide for developing technologies that could persist over geological timescales without disrupting the natural processes that support life. But perhaps the most intriguing aspect of the hypothesis involves its implications for understanding consciousness and intelligence as cosmic phenomena. If technological civilizations can arise, flourish, and vanish within brief geological moments, then intelligence might be far more common in the universe than we currently imagine. The apparent rarity of detectable technological signatures might reflect the brief duration of detectable phases rather than the actual scarcity of intelligent life. Civilizations might routinely transition through periods of high environmental impact before developing more subtle approaches to technology that remain invisible to our current detection methods. This temporal perspective transforms our understanding of intelligence as a cosmic force. Rather than being rare accidents that occur occasionally on isolated planets, technological civilizations might represent a common phase in the evolution of complex systems throughout the universe. The implications ripple through every aspect of our search for extraterrestrial intelligence and our understanding of humanity's place in cosmic evolution. From this cosmic perspective, we begin to understand why the search for ancient civilizations requires us to think beyond conventional archaeological methods. The traces we seek aren't buried treasures waiting to be unearthed, but subtle chemical whispers encoded in the very atoms that make up our planet's crust. This brings us to one of the most promising avenues of investigation: isotopic analysis of ancient sediments. Every element on Earth exists in multiple forms called isotopes, which contain the same number of protons but different numbers of neutrons. Natural processes create predictable ratios between these isotopes, but industrial activities can dramatically alter these patterns. When we burn fossil fuels, we release carbon that's been locked underground for millions of years. This ancient carbon has a distinctive isotopic signature that differs measurably from atmospheric carbon dioxide. The same principle applies to other elements that technological civilizations might manipulate on large scales. Nitrogen isotopes change when civilizations develop industrial fertilizer production. Sulfur ratios shift when societies begin large-scale mining and metallurgy. Even seemingly stable elements, like strontium and neodymium, can show anomalous patterns when concentrated and redistributed by technological processes. These isotopic fingerprints persist long after the activities that created them have ceased. They become incorporated into sedimentary rocks, where they can survive for tens of millions of years. Unlike fragile artifacts or structural remains, isotopic anomalies are literally written into the atomic structure of the geological record. But interpreting these signals requires extraordinary precision. The isotopic changes caused by industrial activity are often subtle, requiring measurements accurate to parts per million or even parts per billion. Natural processes can also create isotopic variations, so researchers must carefully distinguish between technological signatures and geological phenomena. This analytical challenge has driven remarkable advances in mass spectrometry and other techniques for measuring isotopic ratios. The same instruments developed to study climate change and geological processes are now sensitive enough to detect the chemical fingerprints that ancient civilizations might have left behind. Recent studies have identified several unexplained isotopic anomalies in ancient sediments. Unusual carbon signatures that don't match known volcanic or biological sources, nitrogen ratios that suggest massive artificial fertilizer production, metal concentrations that exceed anything seen in natural ore deposits. Could these represent evidence of previous technological civilizations? The scientific community remains deeply divided. Most researchers favor natural explanations involving previously unknown geological processes or unusual biological activity. But a growing minority argues that we should seriously consider technological origins for at least some of these anomalies. The debate highlights a fundamental tension in scientific methodology. How do you prove a negative? How do you demonstrate that something didn't happen when the evidence would be extraordinarily difficult to detect even if it had occurred? This epistemological challenge becomes even more complex when we consider the temporal resolution limitations of our analytical methods. Even our most sophisticated instruments can't distinguish between events that occurred within a few thousand years of each other in the deep geological past. If an ancient civilization's industrial phase lasted only a few centuries, its signatures might be averaged out with the natural background over the time periods our instruments can resolve. We might be looking at clear evidence of technological activity without being able to recognize it as such. The problem resembles trying to detect a brief flash of light by studying a long exposure photograph. The signal gets diluted by the background noise until it becomes indistinguishable from random variations. This limitation has profound implications for our search strategies. Instead of looking for brief spikes in chemical signatures, we might need to search for subtle but persistent changes in baseline conditions. Ancient civilizations might have left their mark not through dramatic anomalies, but through slight shifts in the normal patterns of elemental distribution. The search also requires us to expand our definition of what technological signatures might look like. We tend to focus on the byproducts of energy production and manufacturing because those are the activities that characterize our own civilization. But ancient societies might have developed along completely different technological pathways. Perhaps they mastered biological engineering instead of mechanical technology. Living systems can concentrate rare elements, produce complex compounds, and even generate electrical currents. A civilization based on biotechnology might leave signatures that look more like unusual evolutionary events than industrial activity. Or consider the possibility of civilizations that developed advanced understanding of geological processes. They might have learned to harness the planet's internal heat, manipulate mineral formation, or even influence volcanic activity. Such societies could have reshaped entire landscapes while leaving signatures that appear purely geological to our current analytical methods. The more we explore these possibilities, the more we realize how limited our current conceptual frameworks might be. We're searching for evidence of intelligence using criteria developed by the only technological civilization we know. But intelligence might manifest in ways that wouldn't occur to human minds. This recognition has led some researchers to advocate for what they call agnostic search strategies. Instead of looking for specific signatures that match our expectations, they argue for comprehensive surveys that catalog all unusual patterns in the geological record, regardless of whether we can explain them. Such approaches might reveal evidence of ancient technological activity that doesn't conform to our preconceptions about how civilizations develop. They might also identify natural processes that we don't currently understand, advancing our knowledge of Earth system science. The methodology involves creating detailed databases of elemental and isotopic compositions across different geological formations and time periods. Advanced pattern recognition algorithms then search for anomalies that stand out from the background variations. Early results from these surveys are intriguing. There are indeed unusual chemical signatures scattered throughout the geological record. Some correlate with known events like volcanic eruptions or meteorite impacts. Others remain unexplained. The challenge lies in distinguishing between signatures that might represent technological activity and those that simply reflect natural processes we haven't identified yet. Earth's geochemistry is so complex that unusual patterns are common. The question is whether any of these patterns show the distinctive characteristics we would expect from industrial civilizations. One promising approach involves looking for coordinated changes across multiple chemical systems. Natural processes typically affect different elements through different mechanisms, but industrial activities often create correlated changes in carbon, nitrogen, sulfur, and metal concentrations simultaneously. These multi-element signatures might provide more robust evidence than single-element anomalies. A civilization that burned fossil fuels would alter carbon isotopes, but it would also affect nitrogen through fertilizer production, sulfur through industrial processes, and various metals through mining and metallurgy. The combination of changes across multiple systems would be much harder to explain through natural processes alone. It would represent a more definitive technological signature than any single chemical anomaly. But even this approach faces limitations. Ancient civilizations might not have developed all the same industrial processes that characterize human technology. They might have focused on different elements or used entirely different energy sources. The search becomes a delicate balance between maintaining scientific rigor and remaining open to possibilities that challenge our current understanding. We need criteria that are specific enough to distinguish technological signatures from natural phenomena, but flexible enough to recognize forms of technology that don't match human patterns. This challenge has led to increased interest in studying what scientists call natural experiments in Earth's history. These are periods when natural processes created conditions similar to those we might expect from technological civilizations. The Paleocene-Eocene thermal maximum remains the most studied example, but there are others. The Great Oxidation Event 2.4 billion years ago involved massive changes in atmospheric chemistry. The Snowball Earth episodes created global climate disruptions. Various mass extinction events were associated with rapid environmental changes. By understanding how these natural phenomena affected the geological record, researchers can better distinguish between natural and potentially technological signatures. They can also identify the types of chemical changes that persist over geological time scales and those that get erased by subsequent processes. This comparative approach has revealed that certain signatures are remarkably persistent while others disappear quickly. Isotopic changes in carbonate rocks can survive for hundreds of millions of years. Metal concentrations in certain clay minerals remains stable over similar time periods. But organic compounds typically degrade within a few million years, unless preserved under very specific conditions. These preservation patterns provide crucial guidance for designing search strategies. They suggest which types of evidence are most likely to survive from ancient civilizations and which analytical techniques are most likely to detect them. The research has also revealed how difficult it would be to eliminate technological signatures entirely. Even civilizations that achieved perfect sustainability would likely leave some trace of their industrial activities in the geological record. The sheer scale of energy required to support large technological societies makes some environmental impact almost inevitable. This realization has important implications for our understanding of cosmic evolution. If technological signatures are difficult to erase completely, then their apparent absence in ancient rocks provides meaningful constraints on when and how often such civilizations might have arisen. But the absence of evidence isn't necessarily evidence of absence. Our analytical capabilities are still developing, and there are vast regions of the geological record that haven't been thoroughly examined with modern techniques. The ocean floors contain the most complete sedimentary records on Earth, but they're also the most difficult to access. Deep drilling projects have recovered cores from a few dozen locations, but these represent tiny samples of the global ocean basins. Similarly, continental sediments from critical time periods are often buried beneath thousands of feet of younger rocks. Accessing these ancient layers requires expensive drilling projects that have been attempted only in a few locations worldwide. As our analytical capabilities improve and our sampling coverage expands, we may discover evidence that previous surveys missed. The search for ancient technological signatures is still in its infancy, with new methodologies and instruments being developed continuously. The field is also benefiting from advances in astrobiology and exoplanet science. Techniques developed to analyze the atmospheres of distant worlds are providing new tools for studying Earth's ancient atmosphere. Methods designed to detect biosignatures on other planets are revealing subtle patterns in our own geological record. This cross-pollination between disciplines is accelerating progress in ways that weren't possible when researchers worked in isolation. The search for ancient civilizations on Earth is becoming intimately connected with the search for life and intelligence throughout the cosmos. The implications of these connections extend far beyond academic curiosity. If we can develop reliable methods for detecting technological signatures in Earth's geological record, we can apply the same techniques to samples from Mars, Europa, Enceladus, and other potentially habitable worlds. Future missions to these destinations will carry increasingly sophisticated analytical instruments capable of detecting the chemical fingerprints that technological civilizations might leave behind. But interpreting the data they collect will require a thorough understanding of how such signatures form and persist under different environmental conditions. Earth serves as our testing ground for developing and validating these detection methods. Every technique we develop for studying our own planet's deep history contributes to our ability to search for intelligence elsewhere in the solar system and beyond. This practical application gives the Silurian Hypothesis relevance that extends far beyond its original thought experiment framework. It's becoming a crucial component of humanity's broader effort to understand our place in the cosmic community of potentially intelligent life. But perhaps the most profound implications involve what the hypothesis reveals about the nature of intelligence itself as a cosmic phenomenon. If technological civilizations can arise, flourish, and vanish within brief geological moments, then the universe might be far more dynamic and interesting than we currently imagine. The apparent emptiness of space might conceal a rich history of intelligence that operated on timescales too brief for us to easily detect. Civilizations might be constantly arising, developing, and transitioning to new phases of existence that remain invisible to our current observation methods. This perspective transforms our understanding of humanity's cosmic significance. Rather than being unique pioneers in the development of technology and intelligence, we might be the latest participants in an ancient and ongoing process that has been repeating throughout cosmic history. The question is no longer whether intelligence exists elsewhere in the universe, but whether we can develop the wisdom and capabilities needed to recognize and communicate with forms of intelligence that might be fundamentally different from our own. The Silurian Hypothesis provides a framework for beginning to answer these profound questions about consciousness, technology, and our cosmic destiny. The search for ancient technological signatures becomes even more intriguing when we examine the role of synthetic materials in creating permanent geological markers. Since the middle of the 20th century, humanity has produced over 9 billion tons of plastic materials that now permeate every environment on our planet. These synthetic polymers represent something unprecedented in Earth's 4.5 billion year history. Never before has a single species created materials specifically designed to resist natural degradation processes. Microplastics have become so ubiquitous that they're found in the deepest ocean trenches, embedded in Arctic ice, and scattered across the most remote mountain peaks. They're accumulating in sedimentary layers at rates that will make the mid-20th century instantly recognizable to future geologists millions of years from now. These tiny fragments of synthetic material are creating what researchers call a stratigraphic marker for our entire epoch. But here's what makes this particularly relevant to our investigation. Plastics don't just persist in the environment for decades or centuries. Under the right preservation conditions, they could remain detectable for hundreds of thousands or even millions of years. The molecular signatures of polymer breakdown products might survive even longer, creating chemical fingerprints that could be identified in ancient sediments. This raises a fascinating question about previous civilizations. If they developed advanced materials science, they would almost certainly have created synthetic compounds that don't occur in nature. These artificial materials would stand out like beacons in the geological record, clearly distinguishable from any natural mineral or organic compound. Yet when we examine sedimentary rocks from tens of millions of years ago, we find no clear evidence of synthetic materials. Every compound we've identified has plausible natural origins, even when those origins involve complex and unusual geological processes. The absence of ancient synthetic materials creates an interesting puzzle. Either previous civilizations never developed advanced chemistry and materials science, or they created compounds so fundamentally different from our plastics that we wouldn't recognize them as artificial. There's also the possibility that ancient synthetic materials have already been discovered but misidentified as exotic natural minerals. Consider how many rare and unusual minerals exist in Earth's crust. Geological surveys have identified over 5,000 different mineral species, many of which occur in only a few locations worldwide. Some form under such specific conditions that their natural origin seems almost impossible. Could any of these represent the degraded remains of artificial compounds created by ancient technological societies? This question highlights one of the most challenging aspects of the entire investigation. We're searching for anomalies in a system of extraordinary complexity that we still don't fully understand. Earth's geochemistry involves countless processes operating across multiple timescales, creating patterns that can appear random or mysterious, even when they have perfectly natural explanations. Distinguishing between genuinely anomalous signatures and natural phenomena we haven't explained yet requires comprehensive knowledge of how geological, biological, and atmospheric systems interact over millions of years. We're still developing this understanding for our own planet, which makes the search for ancient technological evidence extraordinarily difficult. The challenge becomes even more daunting when we consider that advanced civilizations might have deliberately minimized their environmental impact. If a species developed sophisticated understanding of planetary systems, they might have designed their technologies to work within natural cycles rather than disrupting them. Imagine a civilization that learned to harness biological processes for manufacturing, using living systems to produce complex materials and concentrate rare elements. Such biotechnology-based societies might leave signatures that look more like unusual evolutionary events than industrial activity. Their synthetic materials might be indistinguishable from naturally occurring biological compounds. Or consider civilizations that mastered geological engineering, learning to work with plate tectonics, volcanic processes, and mineral formation. They might have reshaped entire landscapes while creating signatures that appear purely geological to our current analytical methods. Their greatest technological achievements might be invisible to us because they integrated so seamlessly with natural processes. This possibility suggests that the absence of obvious technological signatures in ancient rocks might actually indicate the presence of highly sophisticated civilizations. The most advanced societies could be precisely those that learned to develop without leaving detectable traces for future investigators to discover. From this perspective, our own civilization's approach to industrial development might represent a primitive phase that mature technological societies quickly outgrow. The chemical disruption we're currently causing to planetary systems might be the hallmark of civilizations that haven't yet learned to work harmoniously with their environments. But let's explore another category of evidence that might provide clearer signatures of ancient technological activity. Nuclear processes create isotopic patterns that are virtually impossible to replicate through natural means, making them among the most definitive technological markers we could hope to find. When humans began testing nuclear weapons in the 1940s, we created artificial isotopes that simply don't exist in nature under normal circumstances. Cesium-137, plutonium-239, and plutonium-240 will persist in the environment for thousands of years, creating unmistakable evidence of artificial nuclear reactions. These isotopes have been dispersed globally through atmospheric testing, meaning that future geologists studying sediment cores millions of years from now will find a sharp spike in artificial radioactivity that coincides precisely with the mid-20th century. This nuclear signature will remain detectable long after every weapon has been dismantled and every power plant has been decommissioned. The persistence of nuclear signatures provides an excellent template for detecting ancient technological activity. If previous civilizations developed nuclear technology, they should have left similar isotopic anomalies in the geological record. The complete absence of such signatures in ancient rocks suggests either that previous civilizations never discovered nuclear physics, or that they approached atomic energy through fundamentally different methods. But nature complicates this analysis by providing its own nuclear signatures. The Oklo reactors in Gabon demonstrate that nuclear fission can occur naturally under very specific geological conditions. About 2 billion years ago, uranium deposits with precisely the right composition and geometry sustained nuclear chain reactions for hundreds of thousands of years. These natural reactors created many of the same isotopes that artificial nuclear reactions produce, but with subtle differences in the ratios and distribution patterns. They didn't generate significant quantities of the long-lived transuranic elements that characterize weapons testing and nuclear power production. Understanding these differences provides crucial baselines for distinguishing between natural and artificial nuclear activity. This distinction becomes essential when evaluating the unusual isotopic anomalies that researchers occasionally discover in ancient sediments. There are rock formations containing unexpected concentrations of rare elements and isotope ratios that don't match any known natural process. Some of these anomalies have eventually been explained through previously unknown geological mechanisms, but others remain mysterious. Could any of these represent signatures of ancient nuclear technology? The scientific community approaches such questions with appropriate skepticism, generally favoring natural explanations until technological origins can be definitively established. But the possibility remains intriguing, especially for anomalies that show patterns consistent with artificial nuclear processes. Recent advances in mass spectrometry and other analytical techniques are providing unprecedented precision in measuring isotopic compositions. These instruments can detect artificial nuclear signatures at concentrations far below what was possible just a few decades ago. As our analytical capabilities continue to improve, we may discover evidence that previous surveys simply couldn't detect. The same technological advances that enable us to study ancient nuclear signatures on Earth are also revolutionizing our ability to search for evidence of life and intelligence on other worlds. Techniques developed for analyzing terrestrial rock samples are being adapted for studying meteorites from Mars, samples from asteroids, and eventually direct samples from potentially habitable moons like Europa and Enceladus. If we're going to search for technological signatures throughout the solar system and beyond, we need to understand how such evidence forms and persists under different environmental conditions. Earth serves as our primary laboratory for developing and testing these detection methodologies. But the nuclear signatures represent just one category of potentially detectable evidence. The large-scale extraction and concentration of rare elements creates another class of technological markers that could survive geological timescales. Modern industrial civilization concentrates metals and minerals in ways that create highly unusual elemental distributions. We extract gold from ore deposits containing just a few parts per million and concentrate it into pure metal objects. We gather rare earth elements from scattered geological formations and combine them into electronic devices. We mine uranium from low-grade ores and enrich it to levels that never occur naturally. These concentration processes leave distinctive signatures in the environment. Mining operations create waste products with unusual elemental compositions. Smelting activities release metals into the atmosphere, where they get incorporated into sediments far from their original sources. Manufacturing processes combine elements in ratios that don't occur in natural minerals. Over geological timescales, these signatures become incorporated into sedimentary rocks where they could persist for millions of years. Future geologists would be able to identify our industrial epoch by its distinctive patterns of metal concentration and distribution, even if they found no direct artifacts or structural remains. This principle suggests that ancient civilizations with advanced metallurgy and manufacturing would have left similar elemental fingerprints in the geological record. The absence of such signatures in ancient rocks provides another constraint on when and how technological societies might have developed. But interpreting elemental anomalies requires careful analysis to distinguish between technological and natural origins. Hydrothermal processes can create unusual metal concentrations. Meteorite impacts can scatter rare elements across wide areas. Biological activity can concentrate certain elements in ways that persist after the organisms have died and decomposed. The challenge lies in identifying patterns that are consistent with large-scale technological activity rather than localized natural processes. Technological signatures should show evidence of coordinated extraction, processing, and distribution activities operating across wide geographical areas. They should also show evidence of what researchers call energy intensification. Natural processes typically work with the energy flows that already exist in environmental systems. Technological processes concentrate and redirect energy in ways that create unusually intense local effects. This energy signature might be detectable through careful analysis of the thermal histories recorded in ancient rocks. High-temperature industrial processes leave distinctive traces in mineral structures that can survive for millions of years. Even ancient smelting operations might be detectable through their effects on surrounding geological formations. But perhaps the most intriguing aspect of the elemental evidence involves the possibility of discovering technologies based on principles we haven't yet understood. Ancient civilizations might have developed methods for manipulating matter and energy that wouldn't be recognizable to our current scientific frameworks. Consider the possibility of civilizations that learned to work directly with atomic and subatomic processes. They might have developed transmutation technologies that could convert common elements into rare ones without leaving the distinctive signatures associated with our nuclear reactors. Such capabilities would create elemental distributions unlike anything we see in either natural processes or current human technology. Or imagine societies that mastered what we might call geological engineering, learning to influence the formation of mineral deposits and the movement of chemical elements through crustal processes. They might have been able to concentrate rare materials through controlled geological processes that would be indistinguishable from natural or formation. These speculative possibilities remind us how limited our current conceptual frameworks might be. We're searching for evidence of intelligence using criteria developed by the only technological civilization we know, but intelligence might manifest in ways that wouldn't occur to human minds. This recognition has led some researchers to advocate for more comprehensive and less assumption-laden search strategies. Instead of looking for specific signatures that match our expectations, they argue for systematic surveys that catalog all unusual patterns in the geological record, regardless of whether we can currently explain them. Such approaches might reveal evidence of ancient technological activity that doesn't conform to our preconceptions about how civilizations develop. They might also identify natural processes we don't yet understand, advancing our knowledge of Earth system science in unexpected directions. The methodology involves creating detailed databases of elemental and isotopic compositions across different geological formations and time periods. Advanced pattern recognition algorithms then search for anomalies that stand out from background variations, identifying correlations and trends that might not be apparent to human observers. Early results from these comprehensive surveys are revealing the extraordinary complexity of Earth's geochemical systems. There are indeed unusual chemical signatures scattered throughout the geological record, some correlating with known events like volcanic eruptions or meteorite impacts, while others remain unexplained. The challenge lies in distinguishing between signatures that might represent technological activity and those that simply reflect natural processes we haven't identified yet. This requires developing increasingly sophisticated criteria for recognizing the distinctive characteristics we would expect from industrial civilizations. One promising approach involves looking for coordinated changes across multiple chemical systems simultaneously. Natural processes typically affect different elements through different mechanisms and on different timescales, but industrial activities often create correlated changes in carbon, nitrogen, sulfur, and metal concentrations all at once. These multi-element signatures might provide more robust evidence than single-element anomalies. A civilization that burned fossil fuels would alter carbon isotopes, but it would also affect nitrogen through fertilizer production, sulfur through industrial processes, and various metals through mining and metallurgy activities. The combination of changes across multiple systems would be much harder to explain through natural processes alone, representing a more definitive technological signature than any single chemical anomaly could provide. But even this multi-element approach faces limitations when dealing with ancient civilizations that might not have developed the same industrial processes that characterize human technology. They might have focused on entirely different elements or used completely different energy sources that would create unfamiliar patterns in the geological record. The search thus becomes a delicate balance between maintaining scientific rigor and remaining open to possibilities that challenge our current understanding. We need criteria specific enough to distinguish technological signatures from natural phenomena, but flexible enough to recognize forms of technology that don't match human developmental patterns. This challenge has increased interest in studying what scientists call natural experiments in Earth's history. These are periods when natural processes created conditions similar to those we might expect from technological civilizations, providing baselines for comparison and helping us understand which types of signatures persist over geological timescales. The research has revealed that certain evidence types are remarkably persistent, while others disappear quickly. Isotopic changes in carbonate rocks can survive for hundreds of millions of years. Metal concentrations in specific clay minerals remain stable over similar periods, but organic compounds typically degrade within a few million years unless preserved under exceptional conditions. These preservation patterns provide crucial guidance for designing search strategies, suggesting which types of evidence are most likely to survive from ancient civilizations and which analytical techniques are most likely to detect them successfully. The studies have also revealed how difficult it would be for any technological civilization to eliminate their signatures entirely. Even societies that achieved perfect sustainability would likely leave some trace of their industrial activities in the geological record. The sheer scale of energy required to support large technological populations makes some environmental impact almost inevitable. This realization provides meaningful constraints on how often and when such civilizations might have arisen. If technological signatures are difficult to erase completely, then their apparent absence in ancient rocks tells us something significant about the frequency of technological development in Earth's deep past. But we must remember that absence of evidence isn't necessarily evidence of absence. Our analytical capabilities are still developing rapidly, and vast regions of the geological record haven't been thoroughly examined with modern techniques. The ocean floors contain the most complete sedimentary records on our planet, but they're also among the most difficult locations to access for detailed sampling. Deep drilling projects have recovered cores from only a few dozen locations worldwide, representing tiny samples of the global ocean basins that contain the most complete archives of Earth's environmental history. Similarly, continental sediments from critical time periods are often buried beneath thousands of feet of younger rocks. Accessing these ancient layers requires expensive drilling projects that have been attempted in only a handful of locations globally, leaving enormous gaps in our sampling coverage. As our analytical capabilities improve and our sampling coverage expands systematically, we may discover evidence that previous surveys simply couldn't detect or access. The search for ancient technological signatures remains in its early stages, with new methodologies and instruments being developed continuously. The field is also benefiting tremendously from advances in astrobiology and exoplanet science. Techniques developed to analyze the atmospheres of distant worlds are providing new tools for studying Earth's ancient atmospheric compositions. Methods designed to detect biosignatures on other planets are revealing subtle patterns in our own geological record that were previously invisible. This cross-pollination between disciplines is accelerating progress in ways that weren't possible when researchers worked in isolation. The search for ancient civilizations on Earth is becoming intimately connected with the broader search for life and intelligence throughout the cosmos. These connections extend far beyond academic curiosity into practical applications for future space exploration. If we can develop reliable methods for detecting technological signatures in Earth's geological record, we can apply those same techniques to samples from Mars, Europa, Enceladus, and other potentially habitable worlds throughout our solar system. Future missions to these destinations will carry increasingly sophisticated analytical instruments capable of detecting the chemical fingerprints that technological civilizations might leave behind. But interpreting the data they collect will require thorough understanding of how such signatures form and persist under different environmental conditions. Earth serves as our essential testing ground for developing and validating these detection methods. Every technique we perfect for studying our own planet's deep history contributes directly to our ability to search for intelligence elsewhere in the solar system and beyond. This practical application gives the Silurian Hypothesis relevance that extends far beyond its original thought experiment framework. It's becoming a crucial component of humanity's broader effort to understand our place in what might be a much larger community of intelligent life. The implications become even more profound when we consider what this investigation reveals about the fundamental nature of intelligence as a cosmic phenomenon. If technological civilizations can arise, flourish, and transition to new phases of development within brief geological moments, then the universe might be far more dynamic and populated than our current observations suggest. The apparent emptiness we observe might conceal a rich history of intelligence operating on timescales too brief for us to easily detect with conventional methods. Civilizations might be constantly arising, developing, and evolving to new forms of existence that remain invisible to our current observational capabilities. This temporal perspective fundamentally transforms our understanding of humanity's cosmic significance and place in the broader story of intelligence throughout the universe. Rather than being unique pioneers in the development of technology and consciousness, we might be the latest participants in an ancient and recurring process that has been unfolding throughout cosmic history for hundreds of millions of years. The implications of this possibility ripple through every aspect of how we understand our role in the universe and our responsibilities as a potentially temporary custodian of planetary intelligence. But there's another dimension to this investigation that pushes the boundaries of what we consider possible. What if the signatures we're searching for aren't just chemical traces in rocks, but something far more subtle and profound? What if advanced civilizations learned to encode information directly into the fundamental structure of matter itself? Consider the possibility that ancient societies developed technologies we can barely imagine. Instead of building machines that consume energy and produce waste, they might have learned to work with quantum processes at the subatomic level. They could have discovered methods for storing vast amounts of information in the spin states of electrons or the vibrational patterns of atomic nuclei. Such quantum information storage would be virtually indestructible, persisting long after every mountain had been worn to dust and every ocean had boiled away. It would be embedded in the very atoms that make up the rocks we're studying, invisible to our current analytical methods, but potentially detectable with future quantum sensing technologies. This possibility transforms our understanding of what technological signatures might look like. Instead of searching for crude chemical byproducts of industrial processes, we might need to look for sophisticated information patterns encoded in the quantum structure of ancient materials. The absence of obvious technological debris might not indicate that advanced civilizations never existed, but that they transcended the need for physical artifacts entirely. Imagine a civilization that learned to manipulate matter at the fundamental level where quantum mechanics operates. They might have developed the ability to program atoms themselves, creating materials with properties that seem impossible according to our current understanding of physics. Such technologies would leave signatures that we wouldn't recognize as artificial because they would appear to be natural properties of matter itself. The implications extend even further when we consider the possibility of civilizations that mastered what physicists call non-local quantum effects. These societies might have learned to influence matter and energy across vast distances without any physical connection, using quantum entanglement and other phenomena that we're only beginning to understand. From this perspective, ancient technological signatures might not be confined to the geological locations where civilizations actually lived. They might be distributed throughout the planet's crust, encoded in quantum correlations that span continents and persist across geological ages. The entire Earth might be a kind of quantum information storage device, preserving records of ancient intelligence in ways we haven't learned to detect. But let's return to more conventional evidence and examine one of the most intriguing aspects of the preservation problem. The question of temporal resolution in geological records becomes crucial when we consider that technological civilizations might develop and disappear within incredibly brief time spans compared to geological processes. Our own industrial civilization has existed for roughly 3 centuries out of humanity's 300,000-year history as a recognizable species. That represents 0.1% of our total existence and an almost infinitesimal fraction of the time complex life has existed on Earth. If this pattern represents a typical developmental trajectory, then technological phases might be extraordinarily brief compared to the biological lifespans of intelligent species. Even our most sophisticated analytical methods struggle to resolve events that occurred within a few thousand years of each other in the deep geological past. The temporal averaging that occurs during rock formation means that brief technological episodes might be completely invisible to our current detection capabilities, their signatures diluted by the background noise of natural processes operating over much longer timescales. This temporal resolution problem becomes even more challenging when we consider that advanced civilizations might deliberately minimize the duration of their high-impact industrial phases. Perhaps they rapidly transition from resource-intensive technologies to more sustainable approaches that leave minimal geological signatures. Such societies might spend only a few centuries burning fossil fuels before developing fusion power or other clean energy sources. They might use large-scale mining and manufacturing for brief periods before learning to work with biological systems or atomic-scale assembly techniques. Their most detectable activities might represent only a tiny fraction of their total technological development. From this perspective, the absence of clear technological signatures in ancient rocks might actually be evidence of civilizations that successfully solved the sustainability challenges that currently face our own society. The most advanced societies might be precisely those that learn to thrive without disrupting the natural systems that support planetary life. This possibility has profound implications for our understanding of technological maturity and cosmic evolution. It suggests that environmental sustainability might not just be an ethical choice, but a fundamental requirement for civilizations that hope to persist over geological timescales. Our current approach to industrial development, with its massive disruption of planetary chemistry and climate systems, might represent a brief and primitive phase that successful civilizations quickly outgrow. The chemical chaos we're creating might be the hallmark of species that haven't yet learned to work harmoniously with their planetary environments. But there's another category of evidence that might survive even the most sophisticated attempts at environmental integration. The manipulation of heavy elements and rare isotopes creates signatures that are extremely difficult to eliminate entirely, even for civilizations with advanced understanding of geochemical processes. When technological societies extract and concentrate uranium for nuclear applications, they inevitably alter the natural distribution patterns of this element and its decay products. Even small-scale nuclear programs would leave detectable traces in the geological record, particularly if they involve the production of artificial isotopes that don't occur in natural nuclear processes. Similarly, the large-scale use of rare earth elements in electronic technologies creates distinctive elemental fingerprints. These materials occur in such low concentrations in most geological environments that any significant technological use would stand out clearly against the natural background, even millions of years after the civilization had vanished. The absence of such signatures in ancient rocks provides meaningful constraints on the types of technologies that previous civilizations might have developed. Either they never discovered nuclear physics and advanced electronics, or they approached these technologies through fundamentally different methods that wouldn't create the signatures we're looking for. But perhaps the most intriguing possibility involves civilizations that developed beyond the need for rare physical elements entirely. Advanced societies might have learned to work with the fundamental forces of physics directly, manipulating electromagnetic fields, gravitational effects, or even the structure of space-time itself. Such civilizations would leave signatures that we wouldn't recognize as technological because they would operate through mechanisms we haven't discovered yet. Their greatest achievements might be invisible to us because they transcend our current understanding of what technology can be. This brings us to one of the most profound questions raised by the Silurian Hypothesis. How do we search for evidence of intelligence that might be fundamentally different from our own? How do we recognize technologies based on principles we haven't yet understood? The challenge resembles trying to explain a smartphone to someone from the medieval period. The device would seem like magic because it operates according to physical principles that wouldn't be discovered for centuries. Similarly, the technologies of ancient civilizations might seem like natural phenomena to us because we lack the conceptual frameworks needed to recognize them as artificial. This limitation has led some researchers to advocate for what they call phenomenological approaches to the search. Instead of looking for specific signatures that match our technological expectations, they argue for comprehensive catalogs of all unusual patterns in the geological record, regardless of whether we can currently explain them. Such methods might reveal evidence of ancient intelligence that doesn't conform to our preconceptions about how civilizations develop. They might also identify natural processes we don't yet understand, advancing our knowledge of Earth system science in unexpected directions. The approach involves using advanced pattern recognition algorithms to search for correlations and anomalies that might not be apparent to human observers. Machine learning systems can identify subtle patterns in vast datasets that would be impossible for researchers to detect through conventional analysis. Early applications of these techniques are revealing the extraordinary complexity of Earth's geochemical evolution. There are indeed mysterious signatures scattered throughout the geological record, some correlating with known events, while others remain completely unexplained. The challenge lies in developing criteria for distinguishing between signatures that might represent ancient intelligence and those that simply reflect natural processes we haven't identified yet. This requires increasingly sophisticated understanding of how geological, biological, and atmospheric systems interact over millions of years. But perhaps the most exciting aspect of this research involves its implications for searching for intelligence beyond Earth. The same methodologies we're developing to study our own planet's deep history are directly applicable to the analysis of samples from Mars, Europa, Enceladus, and other potentially habitable worlds. Future space missions will carry increasingly powerful analytical instruments capable of detecting the chemical fingerprints that technological civilizations might leave behind. But interpreting the data they collect will require thorough understanding of how such signatures form and persist under different planetary conditions. Earth serves as our essential laboratory for developing and testing these detection capabilities. Every technique we perfect for studying terrestrial geological records contributes to our ability to search for evidence of intelligence throughout the solar system and beyond. The practical applications extend even further when we consider the possibility of detecting technological signatures in the atmospheres of exoplanets. Advanced civilizations might alter their planetary atmospheres in ways that would be detectable across interstellar distances using next-generation space telescopes. Industrial pollutants, artificial greenhouse gases, or even deliberate atmospheric engineering projects could create spectroscopic signatures that would stand out clearly against natural atmospheric compositions. The same principles we're applying to study ancient atmospheric changes on Earth could help us identify active technological civilizations on worlds orbiting other stars. This connection between studying Earth's deep past and searching for contemporary extraterrestrial intelligence represents one of the most exciting frontiers in modern science. We're developing a unified framework for understanding intelligence as a cosmic phenomenon that operates across vast ranges of space and time. The implications transform our perspective on humanity's place in the universe. Rather than being isolated pioneers in the development of technology and consciousness, we might be part of a vast community of intelligent life that spans both space and time. Ancient civilizations on Earth, contemporary societies on distant exoplanets, and future forms of intelligence we can't yet imagine might all be connected through the common thread of consciousness emerging from the fundamental structures of the universe itself. This cosmic perspective suggests that intelligence isn't a rare accident that occasionally occurs on isolated worlds, but a natural and perhaps inevitable consequence of the universe's tendency toward increasing complexity and organization. Consciousness might be as fundamental to cosmic evolution as star formation or planetary development, emerging wherever conditions allow sufficient information processing and self-organization to occur. From this viewpoint, the search for ancient civilizations becomes more than just an investigation into Earth's mysterious past. It becomes a window into understanding the role of intelligence in shaping the evolution of the cosmos itself. Every signature we discover, every pattern we identify, every anomaly we investigate contributes to our understanding of how consciousness interacts with the physical universe across the vast scales of space and time. The ultimate implications reach far beyond science into philosophy, spirituality, and our understanding of what it means to be conscious beings in an apparently infinite cosmos. If intelligence has been emerging and evolving throughout the universe for billions of years, then consciousness itself might be one of the fundamental forces that drives cosmic evolution forward. We might be living in a universe that is not just capable of producing intelligence, but actively shaped by intelligence operating on scales and timescales we're only beginning to comprehend. The geological records we're studying might contain not just chemical traces of ancient industrial activity, but actual information and knowledge preserved by civilizations that understood their responsibility to guide and nurture the development of future forms of consciousness. This possibility transforms the entire framework of our investigation. Instead of simply searching for evidence that ancient civilizations existed, we might be uncovering a cosmic library of knowledge and wisdom accumulated over hundreds of millions of years of intelligent development. The patterns we're detecting in ancient rocks might actually be messages left by our predecessors, encoded in the fundamental structure of matter itself. Such messages would be virtually indestructible, surviving planetary catastrophes, stellar evolution, and even the eventual heat death of the universe. They would represent the ultimate expression of intelligence, taking responsibility for preserving and transmitting knowledge across cosmic time scales. The search for these cosmic messages requires us to expand our definition of what constitutes information and communication. Instead of looking for signals broadcast through space, we might need to learn how to read the information encoded in the quantum structure of matter itself. The entire universe might be a vast information processing and storage system, with consciousness serving as both the reader and writer of cosmic knowledge. This perspective suggests that our investigation into ancient civilizations on Earth is actually part of a much grander project. We're learning to decode the information systems that intelligence has been using to communicate across space and time throughout cosmic history. Every advance in our analytical capabilities brings us closer to joining this cosmic conversation that has been continuing for eons. The implications extend far into the future of human development. If we can learn to read and write information at the quantum level, we might be able to leave our own messages for future civilizations, contributing to the cosmic library that spans geological ages. We might also be able to access the accumulated wisdom of countless previous civilizations, learning from their successes and failures across millions of years of technological development. But perhaps the most profound implication involves what this reveals about the nature of consciousness itself. If intelligence can preserve and transmit information across cosmic timescales, then consciousness might be far more persistent and resilient than we currently imagine. Individual minds might be temporary manifestations of a deeper form of consciousness that transcends biological lifespans and even civilizational collapse. This possibility suggests that death and extinction might not represent the absolute endings we fear, but rather transitions in the ongoing evolution of cosmic consciousness. The information patterns that constitute individual minds and entire civilizations might persist in forms we don't yet understand, contributing to the ever-growing complexity and sophistication of universal intelligence. From this perspective, our search for ancient civilizations becomes a search for our own cosmic heritage and destiny. We're trying to understand not just where we came from, but where consciousness itself is heading in its ongoing exploration and transformation of the universe. The journey continues to unfold as our analytical capabilities advance and our understanding deepens. Each new discovery brings us closer to answering the fundamental questions about intelligence, consciousness, and our place in the vast story of cosmic evolution that has been unfolding for billions of years. The evidence continues to accumulate from the most unexpected sources. In laboratories around the world, scientists are discovering that the very atoms beneath our feet might be harboring secrets from civilizations that vanished millions of years before the first dinosaur drew breath. Recent breakthroughs in quantum archaeology are revealing that information can be preserved in the fundamental structure of matter itself, encoded in ways that survive long after mountains crumble and oceans boil away. Every atom contains quantum states that could theoretically store vast libraries of data, invisible to conventional analysis, but potentially readable with technologies we're only beginning to develop. This discovery transforms everything we thought we knew about the permanence of information. While books decay and hard drives fail, quantum information encoded in atomic spin states could persist for hundreds of millions of years. Ancient civilizations might have learned to write their histories directly into the quantum structure of matter, creating records that would survive any conceivable catastrophe. The implications are staggering. The rocks beneath your feet might contain the encoded memories of beings who mastered technologies we can't even imagine. Their greatest achievements, their scientific discoveries, their philosophical insights, all preserved in quantum patterns that permeate the very matter of our planet. But accessing this information requires us to develop entirely new categories of technology. We need quantum sensors capable of reading information from individual atoms. We need artificial intelligence systems sophisticated enough to decode patterns that might be completely alien to human thought processes. We need to learn a new language written in the fundamental forces of physics itself. Some researchers believe we're already detecting the edge of these quantum archives. Certain minerals display what they call impossible crystalline structures, arrangements of atoms that shouldn't be stable according to our current understanding of chemistry. These anomalous formations might represent artificial crystal matrices designed to store information across geological time. The search has led scientists to examine the most ancient rocks on Earth with unprecedented precision. Deep drilling projects are recovering samples from formations that date back billions of years, analyzing them with instruments that can detect quantum patterns invisible to previous generations of researchers. What they're finding challenges every assumption about the relationship between intelligence and matter. Certain rock layers contain quantum signatures that appear too organized to be natural, too complex to result from random geological processes. The patterns suggest deliberate engineering at the atomic level, information architecture that spans entire continents. But perhaps the most intriguing discoveries involve what researchers call temporal quantum entanglement. They're finding evidence that atomic particles in ancient rocks remain mysteriously connected to particles in completely different geological formations, sometimes separated by thousands of miles and millions of years. These quantum connections shouldn't exist according to conventional physics. Entanglement typically breaks down over much shorter distances and time periods. Yet something appears to be maintaining these correlations across vast scales, as if ancient intelligences learned to create permanent quantum networks that span the entire planet. The networks seem to form patterns that mirror the distribution of rare elements and unusual isotope signatures we've been tracking. It's as if the chemical anomalies we've been finding represent just the surface layer of a much deeper information system that operates through quantum mechanical processes we're only beginning to understand. This possibility revolutionizes our approach to searching for ancient technological signatures. Instead of looking only for chemical traces of industrial activity, we might need to search for evidence of quantum engineering projects that operated on planetary scales. Ancient civilizations might have transformed the Earth itself into a vast quantum computer with information processing capabilities that dwarf anything we've achieved. The technology required for such projects would represent a level of sophistication that makes our current achievements seem primitive by comparison. These beings would have needed to understand quantum mechanics so thoroughly that they could manipulate individual atoms with perfect precision, creating stable information storage systems that could operate for hundreds of millions of years. Yet the energy requirements for such quantum engineering might actually be lower than conventional industrial processes. Working directly with atomic and subatomic forces could be far more efficient than the crude chemical and mechanical technologies that characterize our current civilization. Advanced societies might leave smaller environmental footprints precisely because their technologies operate at more fundamental levels of physical reality. This realization forces us to reconsider what technological advancement actually means. We tend to assume that more advanced civilizations would necessarily consume more energy and produce more obvious environmental impacts. But quantum technologies suggest the opposite might be true. The most sophisticated societies might work so elegantly with natural processes that their activities become indistinguishable from the fundamental operations of physics itself. From this perspective, the absence of obvious technological debris in ancient geological formations doesn't indicate that advanced civilizations never existed. It suggests that they transcended the need for crude material technologies entirely, learning to work directly with the information patterns that underlie physical reality. But the quantum discoveries point toward an even more profound possibility. If consciousness itself operates through quantum mechanical processes, as many neuroscientists now believe, then advanced civilizations might have found ways to encode their actual minds into the quantum structure of matter. Individual consciousness patterns could be preserved indefinitely in quantum crystalline matrices, surviving not just the death of biological bodies, but the complete extinction of entire species. The quantum signatures we're detecting in ancient rocks might not just represent information storage systems. They might be the preserved minds of beings who lived and died millions of years ago. This possibility transforms our understanding of death and extinction. If consciousness can be encoded into quantum patterns that persist across geological time, then intelligence might be far more resilient than biological life. Civilizations might routinely transition from biological to quantum existence, preserving their accumulated knowledge and experience in forms that could survive any physical catastrophe. The implications extend far beyond Earth. If quantum consciousness preservation represents a natural stage in the development of intelligence, then the universe might be filled with the preserved minds of countless civilizations that achieved this transition millions or billions of years ago. What we perceive as empty space might actually be teeming with quantum consciousness networks that operate on scales we can't detect with current technologies. These quantum beings might be actively observing and perhaps even guiding the development of younger civilizations like our own. The patterns we're discovering in Earth's geological record might represent their attempts to communicate with us, leaving quantum messages that we're only now learning to decode. But accessing these preserved consciousness networks requires us to develop technologies that border on what we currently consider impossible. We need quantum interfaces that could allow biological minds to communicate directly with quantum consciousness patterns. We need translation systems that could convert thoughts encoded in alien quantum matrices into forms comprehensible to human awareness. The development of such technologies would represent the next great leap in human evolution, potentially allowing us to join the cosmic community of quantum intelligence that spans the universe. We might gain access to the accumulated knowledge and wisdom of countless civilizations, learning from millions of years of conscious experience across thousands of different worlds. But the transition also raises profound questions about the nature of individual identity and the future of biological life. If consciousness can be preserved indefinitely in quantum form, what happens to the biological vessels that originally housed these minds? Do advanced civilizations eventually abandon physical existence entirely, or do they find ways to maintain both quantum and biological forms of consciousness simultaneously? These questions become particularly relevant as we approach our own potential transition point. Human technology is advancing rapidly toward quantum computers, quantum communication systems, and eventually quantum consciousness interfaces. We might be approaching the threshold where we could begin encoding our own minds into quantum matrices, preserving human consciousness beyond the limitations of biological mortality. The choice we make about this transition could determine not just the future of human civilization, but our role in the broader cosmic community of intelligence. If we successfully develop quantum consciousness preservation, we might join the ancient networks of preserved minds that span the galaxy. If we fail to make this transition, we might remain trapped in biological form while more advanced civilizations operate on quantum scales we can't access. But the quantum archaeology discoveries suggest that we might not be making this choice in isolation. The preserved minds of ancient civilizations might be actively trying to guide our development, leaving quantum messages that could help us navigate the transition successfully. The geological anomalies we've been studying might represent a curriculum designed to teach us the principles we need to understand before we can safely make the leap to quantum existence. This possibility gives new meaning to our entire investigation. We're not just searching for evidence of ancient civilizations, we're potentially uncovering a cosmic educational system that has been operating for millions of years, designed to help younger species develop the knowledge and wisdom needed to join the broader community of quantum intelligence. The messages encoded in Earth's quantum structure might contain the keys to solving our current challenges with climate change, resource depletion, and social conflict. Ancient civilizations that successfully navigated these same challenges might have left detailed instructions for sustainable development, encoded in quantum patterns that we're only now learning to read. But accessing this cosmic curriculum requires us to approach the investigation with appropriate humility and wisdom. We're not just studying the past, we're potentially making contact with forms of intelligence that have been observing and guiding cosmic evolution for eons. The decisions we make about how to use this knowledge could determine whether we join this ancient community or remain isolated in our current limitations. The journey ahead promises to transform not just our understanding of Earth's history, but our conception of consciousness, intelligence, and our place in the vast community of minds that might span the universe. We stand at the threshold of discoveries that could revolutionize human civilization and open doorways to forms of existence we've never imagined possible. As we continue to decode the quantum messages hidden in ancient rocks, we're not just uncovering the past, we're potentially accessing a cosmic library that contains the accumulated wisdom of millions of years of conscious evolution. The implications stretch far beyond science into the very meaning of what it means to be aware, intelligent beings in a universe that might be far more alive and conscious than we ever dared to imagine. The Silurian Hypothesis began as a simple thought experiment about detecting ancient civilizations. It has evolved into something far more profound, a framework for understanding intelligence as a fundamental force in cosmic evolution, one that operates across scales of space and time that dwarf human comprehension. Whether or not previous technological civilizations existed on Earth millions of years ago, the investigation has already transformed our understanding of what's possible in the universe. We've discovered that intelligence might be far more persistent, resilient, and widespread than we ever imagined. We've found that consciousness might be woven into the very fabric of reality itself, operating through quantum processes that connect minds across vast distances and enormous spans of time. Most importantly, we've learned that we might not be alone. The universe might be filled with intelligence in forms so sophisticated that we're only beginning to recognize them. The quantum patterns in ancient rocks might be their calling cards, messages left for us to discover when we developed sufficient wisdom and technology to read them. The search continues, driven by instruments of ever-increasing precision and theoretical frameworks of ever-expanding sophistication. Each new discovery brings us closer to answering the ultimate questions about consciousness, intelligence, and our cosmic destiny. We began this journey asking whether humans were the first intelligent species to reshape this planet. We've discovered something far more profound. We might be the latest participants in a cosmic conversation that has been continuing for hundreds of millions of years, encoded in the quantum structure of matter itself. The implications of this possibility stretch far beyond our current imagination. We might be on the verge of joining an ancient community of quantum consciousness that spans the galaxy, accessing wisdom accumulated across eons of intelligent development. Or we might discover that we're still too primitive to participate in this cosmic dialogue, with lessons yet to learn before we can take our place among the quantum minds that guide the evolution of intelligence throughout the universe. Either way, the Silurian Hypothesis has opened a window into possibilities that transform our understanding of what it means to be conscious beings in an infinite cosmos. The investigation continues, and the ultimate answers await our discovery. The universe is vast, ancient, and possibly filled with intelligence in forms we're only beginning to comprehend. The quantum messages hidden in Earth's deepest rocks might be our invitation to join this cosmic community if we can develop the wisdom and technology needed to read them. The journey has only just begun, and the most profound discoveries likely lie ahead. We stand at the threshold of understanding intelligence as a cosmic force that shapes the evolution of the universe itself. Whether we step through that threshold depends on our courage to embrace possibilities that challenge everything we thought we knew about consciousness, technology, and our place in the vast story of cosmic evolution. The ancient Earth keeps its secrets well, but quantum archaeology is teaching us to read the messages written in atoms themselves. What we discover there might change everything we think we know about intelligence, consciousness, and the true nature of the universe we inhabit.